So let's take a look at our write-up for the experiment that is scheduled for today. And you will need Excel or some spreadsheet, okay? And the spreadsheet that I have here is an Excel spreadsheet. Let me find that real quick. Here it is. It's in the bottom. The first thing that you want to do, if you have Excel, or you can just watch it in this replay of Zoom, is the following. Now let me just zero in on this particular page because that's where we're going to be spending a lot of our time. So I'm going to zero in on this Excel spreadsheet. Now the data that you see here is not the data that you guys are going to, it's not the data in the video. These are other data that I've recorded in the past. I only use this as an example of what you guys need to do for the calculations. So do not try and replicate this and submit it as your answer. It's going to be wrong, and then you won't get any credit. What you do need to do is put the data that you guys are able to collect from the video in a template like this. You've got trial 1, 2, 3, 4, and then the standard, which is test tube 5. You guys have an absorbance for each one, and that's actually shown on a chart. You need to write down the absorbance and then the absorbance of the fifth solution, okay? And then you need to figure out the initial concentration. The initial concentrations for test tube 1, remember that the concentration of the iron nitrate is 0.002, 0.002. But then you have a dilution factor. So let me try and explain what's going on here so that you guys can see the calculation. So the iron nitrate on that first solution, FeNO3, 3 times, that's why it's an iron 3. Okay, because the nitrates are spectator, but the concentration of this is 0.002. And you use 5 milliliters of it. In fact, for all 4 test tubes, you use 5 milliliters of the iron nitrate.
We're still on the Excel sheet.
Oh, sorry. Thanks. Yeah, sometimes I'm looking at my screen and I forget that you guys are not seeing the same thing on my screen. Thanks for letting me know. Always keeping me honest. Here, I'll give you this. Okay. Now you should see both my both my iPad and my spreadsheet. So these are test tubes 1, 2, 3, 4. Remember the total volume that we prepared was 10 milliliters. So we use 5 milliliters of 0.002 molar for each, and we added enough counter solution, whether it be water or potassium thiocyanate, to have a total of 10 milliliters. So the concentration of iron nitrate is 0.00200 moles per liter times 5 milliliters in a total volume of 10 mils. So that's the concentration. This was your pre-lab question, by the way, of that iron nitrate is going to be that, okay? And that's going to be true for all of them because we're using 5 milliliters of iron nitrate in all 4 test tubes. The 5th test tube, however, we use 20 milliliters. And the concentration there was 0.200 molar of iron nitrate. And we use 18 milliliters, okay? If you watch the video, in that Eppendorf pipette, I dialed in 10. I added 10 milliliters to that big test tube, and then I dialed in 8 10 plus 8 is 18. So the concentration of iron here is 0.200 moles per liter times 18 divided by 20. The milliliters cancel and you get a molarity. For the first solution here, in terms of the potassium thiocyanide, okay, for potassium thiocyanide, KSCN, I believe KSCN, potassium thiocyanide, okay? The potassium is a spectator. But I believe in that first test tube, we only used 2 milliliters of that solution. We used 2 here, 3 here, 4 here, and 5 milliliters on the 5th one. So the concentration of potassium thiocyanide was 0.0020 moles per liter. And we use 2 mils in 10 milliliter volume. So that's a concentration of potassium thiocyanide in that first test tube. In the second test tube, we didn't use 2, we used 3. So you change this to 3 and you do the calculation for that test tube. But for the third test tube, we didn't use 3, we used 4. So you multiply it by 4 over 10. And finally, the fourth test tube, we use 5. So you take the concentration, multiply by 5 over 10. Here, we use 2 milliliters to make it a total of 20. But the concentration of the potassium thiocyanide was still 0.0020 molar. Okay? It was the same concentration as the other 4. But we only use 2 milliliters in 20. So that's the concentration of your standard in here. Okay? So you guys should be able to calculate that right here. That's what you guys are going to be putting in these columns right here. The iron initial concentration, the thiocyanide initial concentration, as well as the standard, and then you're writing the absorbance as observed in the video. So let me take you to a different page. Now want to make sure that you guys understand this because it's critical. This is just, again, a template of your calculation. In this particular example, the concentration of the potassium thiocyanide is 0.004. The concentration of the iron nitrate, the diluted one, the weaker concentration is 0.0025, and the concentrated one is 0.25. Guys, remember that for your experiment, it was 0.002 for the potassium thiocyanide, it's 0.002 for the lower concentration of the iron nitrate, and 0.2 for the high concentration of the iron nitrate. I'm using different numbers here, but the calculation steps are still the same. Okay, so how did I get 0.008? Well, right here, if you click on that, it says it's 0.004 times 2 divided by 10. That's because we're using a 2 mil aliquot. Aliquot is the portion of chemical that I'm using in a 10 mil. Okay, 2 over 10 is the dilution factor. Whenever you add more water into a solution, it's going to be more dilute. That's the dilution factor. We're using 2 mils of thiocyanide in 10 mils total volume. So the different concentrations are going to change and it's going to go up each time. I could also calculate the concentration of thiocyanide for my standard, but that's not as critical, and I'll explain why. You notice that the iron plus 3 are all identical. Why? Because if you look at my comments here, you're taking 0.0025. That's the concentration that I said my iron nitrate was. and you're multiplying it by 5 and dividing by 10. That's your dilution factor. So the concentrations for those 4 test tubes are the same. This one's a little bit tricky. The question is, well, isn't the iron initial going to be the, it's not really the iron initial, it's going to be the iron that reacts. And that, let me try and explain what's going on here. Why am I using this number? So let me explain to you what's going on, because this is the difficult part. The large test tube had, for this, 0.25 molar. And I'm using 18 in 20 milliliters, okay? So in here is my iron plus 3, and that's my 18 mils. So the iron in here is that amount. The FeSCN in here is according to my numbers, 0.004 times 2 over 18. Okay, that's the concentration. The key here is that when this reaction occurs, this is the limiting reagent. Let me try and show you this right here. The iron plus 3 plus FeSCN goes to FeSCN plus 2. Okay, that's the reaction that occurs when you mix the two. As soon as you add the thiocyanide, you form this right here. And this will be at equilibrium. So here we have this initial concentration, whatever this number is. We have this initial concentration, whatever this number is. This is 0. And this is minus X. But because the thiocyanide is so much lower compared to the iron, that's your limiting reagent. So whatever that quantity is, whatever that concentration is, it's all going to get consumed. It's all going to get consumed. And so that amount that gets consumed is also that amount that gets consumed from the iron. And it's that amount that is produced for the iron thiocyanide because it's a limiting reagent. It's not exactly the same, but it's pretty much a very close approximation. Because when you increase the iron 100 times more than the thiocyanide, then Le Chatelier's principle will dictate that the thiocyanide gets almost all consumed to produce products. So at equilibrium, this concentration is the concentration of the iron thiocyanide. So that's why I have it right here. Okay, that concentration of thiocyanide is this concentration right here. That's also the concentration of my iron thiocyanide at equilibrium. It really, to be clear, this thing should really be over here. Oops. Should be, this cell should really be over here. Because that's the equilibrium concentrations of these things. Okay, so now how do we determine the equilibrium concentration for each of these 4 reactions? Well, if you go back to the PowerPoint, this is what I showed you. A1 over A standard equals the concentration of FeSCN for solution 1 divided by FeSCN for the standard. And this is at equilibrium. What we want is this guy right here. We want that guy right here, because that's what we want to input right in here. We want that number in this cell right here. So how do we calculate that? Well, we know what this is. According to our table here, that's just 0.234. We know what this is. According to our table here, that's just 0.8858. And we know what this is. According to our table there, that's 4.0 times 10 to the minus 4. That now, when we multiply that together, is equal to my iron, FeSCN, at equilibrium for solution 1. We're just using that relationship. So that's what I'm going to do. I'm going to put in here equals this cell. So I'm just going to click there, divided by this cell times this right here. And then I'm going to hit return. Okay, so that's my equilibrium concentration of iron thiocyanide for the first test tube. Now I'm going to do a propagation of calculation, and I want to hold this concentration constant because look what happens. The way you do a propagation of calculation, remember, is you click on that, go to the right corner, hold down that key, and then drag it down. And when you do that, you get that. And the reason why you're doing that is because it's taking these values and dividing by, let me just show you what's going on. Like highlight that. See how it's taking these two values and it's dividing by that? That's because it's doing a relative cell. Okay, it's a relative cell. So I actually have to fix these points. And the way I fix these points is I put dollar signs. So I need to put a dollar sign. So the way I do that is I go back to the original. I don't want to change B2 because B2 is fine, but I do want to fix B6. So I'm going to put, when you're propagating down, you put the dollar sign after the letter. And then I also want to put a dollar sign after the letter E. And that way it holds that cell constant. Now, if I do a propagation of calculation, everything should be fine. Okay. So that's how you do that. You got to make sure that the formula is pointing to the right cell. And the dollar sign after the letter means that if you're going to go downwards in your propagation of calculation, it's constant for that particular cell. If you're going to go across in your propagation of calculation, then you put the dollar sign before the letter. Before the letter for across, after the letter going down. So that's the iron thiocyanide concentrations for each of these reactions, if that's my concentrations for each of these solutions. Now the equilibrium iron, that's when the reaction's complete. What's the equilibrium iron? It's going to be the initial minus how much is used up. How much is used up is equal to how much forms. So I'm just going to take here equals the amount that I have minus the amount that actually gets used up to form the iron thiocyanide. And so it's a simple equation, D2 minus E2, and I hit return. And that's how much iron 3 is left when the reaction is completed. Then I'm going to do a propagation of calculation. Okay, and they all should be fairly similar to each other. The thiocyanide is the same. It's how much I start with minus how much is used up. So again, it's going to be equals, I start with this, the amount that I use is this, and I just have to hit return, and I can just do the propagation of calculation here. And what will happen is I would get something like this right here. This is the, let me just double check something. Okay, I see the problem. You guys should spot it too. This is the using the wrong cells. The concentration of thiocyanide at equilibrium is the initial minus the equilibrium thiocyanide. It's not minus the iron at equilibrium. See how I made a mistake? I took this minus that. It's actually this cell minus that cell. So I can do that. I can fix this by just clicking on this and then dragging this over. See how the formula goes from C2 to E2 now? Release, and it fixes itself. That number is now positive. I'm going to do a propagation calculation here. And that's my thiocyanide concentration at equilibrium. So how do I calculate Kf? Kf is equal to products divided by reactant. So this is what it'll look like, but let me show you how to set up that calculation. So again, you want to start with an equal sign, telling Excel that it's an equation, and then just click on these things. It's products, which is this. See how this thing fills to E2? Divided by, and put a parentheses, this quantity times this quantity, return, right parentheses, and then hit return. So that's my concentrations for, or my Kf for test tube 1. And because these things are being carried at the same temperature, they all should be very close to each other, okay, within experimental error. We're going to do a propagation calculation. Okay, so about 145 plus or minus, and again, it's going to vary. It's not always going to be the same because maybe the temperature fluctuated or maybe the concentrations aren't exact, but that's why you do the experiment. Experiments are not always going to give you the exact theoretical value, but it should be close. It should be very close. So what we're going to do next is we're going to take an average. So average equals, and then I'm also going to do a standard deviation. So I'm going to put that in the next line, STD-DEV. The standard deviation tells you how close your values are to the average. The bigger the spread, the less precise you are. The narrower the spread, so the smaller the standard deviation, the better precision you have in your experimental results. So that's why we always like to do statistical analysis in data, because we want to see how well we did the experiment. So the way you do average is you click on the place where you want to do the calculations, equals, again, it's telling Excel that you want to do an average calculation. So I'm going to type equals, and then AV right here, average. And then it's going to ask you for numbers that you're going to average. It's going to give you that. So it already has the parentheses. All I've got to do is click the array of the data that I want to average. And then all I've got to do is hit return. Okay. So that's the average, 145.91. These things are measured out to, it really should be measured to about 3 significant figures, because all your concentrations should have 3 significant figures. If you look at the bottle, the reagents were 0.00200, 3 significant figures. So you should round these things off to 3 significant figures, because that's the concentrations that you were doing. In terms of the standard deviation, I won't do that here, but I told you to do that in your results, so make a note. In order to do the standard deviation, it's as doing the average. That's why I love Excel. Okay, you click on that cell, type equals, and then just type STDEV, and that's this right here. the shorthand notation, or the abbreviation for standard deviation is STD, standard. SD, standard, DEV, deviation. And then we want to click the array again. And then hit return. So the average is 195.81 with a plus or minus 10. If you take a look at this right here, that's about 156. That's about 10 higher than 145. And 132 is about 10 lower than 145. So again, the standard deviation is about plus or minus 10 for this particular experiment. So that's basically the calculation. This is a very easy experiment. The calculations are easy. You just got to make sure that you know your basic chemistry and know how to do concentration calculations. And then the concept here as to what's going on, how we calculate the equilibrium concentration, that goes back to this right here. Okay, it goes back to this because it goes back to Beer's law. Beer's law tells you the absorbance for any chemical is equal to the epsilon times the path length times the concentration. Well, we're using the same chemical, so the absorptivities are the same. We're using the same cell, so that's going to be the same. So we can say that the absorbance is directly proportional to the concentration. And if we have another one in which we have the standard, remember the reason why we have the standard is so that we know exactly how much product is produced. This we don't know. This we don't know. That's a question mark. But this we definitely know because we control the experiment so that the limiting reagent tells you how much of the product you know. So this standard concentration we know, and so we can calculate the unknown by just doing the simple math. Okay. So in the end, when you guys do this, you guys will probably complete a spreadsheet like this. Your numbers are going to be different because again, the concentrations that I'm using here and the absorbance that I'm using here are different from your data, but the methodology are identical. The methodology is identical. When you finish this, you need to talk about what this result means, okay, in the context of the reaction that you are studying and the observations that you made. Are there any